Welcome to Lecture 10 in our second semester class on stochastic processes. Today we start discussing the case of reversible Markov chains, or reversible Markov processes to be correct, which is an extension of the case of a reversible Markov chain to continuous time. And we shall see that in this case we have many interesting, really very tractable and practical techniques at our disposal which help us to analyze such processes. And the basic definition that will be our starting point is the following, namely that let xt be a Markov process in continuous time on a general state space. Then this Markov process is called reversible if for any fixed time, capital T, the law of the process, when restricted to time in the interval from 0 to capital T, is the same as the law of the process which is obtained by running backwards in time. But here backwards in time means that we run backwards starting from this capital time point, from this time point capital T, and run the trajectories backwards in time. If this process has the same law as the initial process, which is just a forward process, then we call the process reversible. And if you write down what that means in actually finite dimensional distribution, it means that if you fix a collection of ordered time points t1 to tn, and you consider the law of these finite dimensional, or you just consider the finite dimensional distribution of these trajectories when evaluated at these finite number of time points, then this finite dimensional distribution is the same as if you evaluate the process at the time points which are obtained by running backwards in time and doing this inflection with respect to the time points. So here you see that you really run backwards in time because these numbers, these time points at which you evaluate the trajectories, are actually decreasing. So therefore this is a backwards trajectory that you evaluate on this side, and here you evaluate the forward trajectory on the corresponding time points. The concept of reversibility of Markov processes or stochastic processes in general generalizes the idea of a dynamical system, of a continuous dynamical system, which is invariant under time inflection. This way we describe the invariance under time inflection not in terms of a trajectory-wise identity, which would be the case for the deterministic system. Here we want to consider that, or we want to require that at least the laws, so the statistical properties of these two processes are the same. And from a physical point of view, this signifies that this stochastic process, which describes some physical behavior of a system or so, is in a dynamic equilibrium, which means that it is an equilibrium under these forward-backward inflection. Here comes the main step towards our analytical description of reversibility of processes, namely, suppose we have a Markov process, a Markov chain, a Markov process on a general state space with the transition function pt, and assume that mu is the initial distribution of this process, so just the law of the process at time 0, then this process is reversible if and only if, first, this law is invariant under the action of the corresponding transition function, and secondly, we have the following symmetry condition, which says that if for any measurable subsets in our state space, the following expression is symmetric, namely we can hit the indicator function of the set B with the transition function P at any time t, and we can take this in the L2 inner product with respect to that measure mu. Then the claim is that this quantity is the same if the roles of the sets A and B are interchanged, which means that this quantity on this side is the same as if we hit the indicator function of the set A with the PT function first, and then take this resulting mu function in the inner product with the indicator function of the set B, where we use the inner product which is induced on functions on our state space as the L2 inner product with regards to the determined measure mu. So here we use the notation that the bracket of a function f with the function g in this mu bracket, that is just the notation for the integral of the product of the two functions f and g against the mu measure, which is basically the L2 inner product on functions with regards to this weighting measure mu. And sometimes we also shall use the notation that just the f in the inner product, or the f in the angle with, or the bracket with the mu, is then just the full integral of f with regards to mu. Okay, so let me give the statement again. We say, that's the statement of the proposition that we're going to discuss now. The process x on the Markov process x on a general state space is reversible if and only if the initial law of the process is invariant, and secondly, that these transition kernels, when interpreted as operators on function space, when these transition kernels for any time t are symmetric operators on the function space, when we work with the L2 inner product on function space with the weighting measure mu. Okay, we sketch the proof of that. We start with a reversible Markov process, and sometimes I shall also call a reversible Markov process a symmetric Markov process, which is a little bit of an abuse of a notation, but that might happen nevertheless, that I sometimes use that name as well. So first I would like to check that the law of the process, or the initial distribution of that process, is actually invariant. Well, that's easy to show. We know that the law of xt can be written, of course, trivially as the law of the process x at time t minus 0, but by the time inflection invariance, this is the same as the law of the process as x naught at time naught, which is defined to be mu. So we see that mu is also the law of the process at time t, which means that mu is in fact an invariant measure. Now, we want to show that this transition operator is in fact a symmetric operator in this weighted L2 space. For that purpose, we write down the joint probability that for these sets A and B at initial time, the process is in the set A, and at time t, the process is in the set B. And this has the representation as the integral of the kernel measure of the set B when integrated with respect to the first argument of the kernel integrated against the measure mu, which is the initial distribution of the process by definition. And of course, this can also be written just by our notation as this bracket expression. It's the indicator function of A integrated against the action of the PT operator acting on the indicator function of the set B, and the whole thing integrated against the measure mu. Well, and again, by time inflection, we know that the probability that we started with is just as good as if we do in time inflection with respect to the time point capital T equals little t. So therefore, this probability is the same as if we ask that at the time little t, the process is in the set A, and at initial time, the process is in the set B. And by the same considerations, we obtain this expression here, which is just writing out this probability in terms of our transition function and the initial law. And now, since the two probabilities are the same by definition of reversibility, we can also conclude, of course, that the two expressions, the two brackets, are the same, which is exactly the claim of symmetry of this operator P in this weighted L2 space. Now we want to go in inverse direction. We want to show that if the measure is invariant, and if the transition kernel or the transition functions for any time t have the symmetry property, then the process is reversible. So for that purpose, I shall restrict to a special case when I have only 3 time points, and I fix a certain time, capital T. And let us consider the case that we ask for 3 different time points, the process to be in a certain subset A, or is in a certain subset B, and a certain subset C, respectively. Then, by our representation of these transition probabilities, or these distributions, or the final dimensional distributions of the process, in terms of the initial law and in terms of the transition function, we can write this probability as the integral against the measure mu of these nested applications of these semigroup or transition kernels, when at the different levels we have to insert the corresponding indicator functions. So this one here, for instance, represents the probability to jump from a certain point to the set C in the time interval, or in the time step from T3, correction from T2 to T3. That's the probability to do such a transition, and this needs to be multiplied with the indicator function of B, which basically says that this is the event. This describes the probability of the event that we start from a point in the set B that then needs to be multiplied with this transition operator at the time point T2 minus T1 and so forth. And so therefore this is this nested expression. Well, we can now apply the adjoint operation, or we can just move the operation of PT by definition of the adjoint operation. We can move that towards an operation on the mu, which is just another way of representing this operation. So in other words, we have on the left-hand side now the adjoint of this P operator at time t minus 1 acting on the measure mu, and on the right-hand side we have everything that was inside this outermost bracket. But by invariance of the measure mu with regards to the application of the P star operation, this mu, of course, then remains unchanged. And therefore, this simpler expression remains. And we can now multiply, if you like, or just pass to the representation of this bracket as the inner product of the indicator function of A with this operation of the PT2 minus T1 operator acting on the interior when considered in this weighted L2 space. And now by symmetry we can move this PT operator onto this indicator function, which yields then this representation here. So we have PT2 minus T1 acting on 1A multiplied, and then in the inner product with the 1B times everything that remains after that. And we can iterate this procedure by multiplying the 1B, or the indicator function of the set B. We can just consider this as a multiplication on the left-hand side. So we just move the multiplication operator on the left part of this bracket. And then on the right-hand side, again, we have an expression which involves an operation of a PT on some function alone in the inner product of mu. And again, we move the T3 minus T2, so this operator we move onto the left-hand side. So this continues, and ultimately we move again the indicator function of 1C onto the left-hand side, such that we are left with this expression here. And now we can insert, now we basically unwind in a way these operations as follows. We insert, or we replace the mu here in this bracket. We replace this by PT minus T3 star of mu, which is the same as mu by invariance. And therefore we can hit this whole expression here, which we have in the left-hand side of the bracket. We can hit that with the operator P for the time T, capital T minus T3. And then we can, basically we have the full expression that we would like to see. Namely, finally we replace these differences of T3 minus T2 and T2 minus T1. We can write them equivalently as a capital T minus T2 minus a capital T minus T3 And likewise, we can write this difference as a difference of a capital T minus T1 minus a capital T minus T2. And if we look at what we have here, we have these time points T and so forth. These are increasing time points, and we see that by our representation of finite dimensional distributions by means of these transition kernels and the initial measure mu, we see that the thing that we have written here can also be interpreted as the probability for our process to be at the first of these times in the set C, and then at the second of these times, which is capital T minus T2 in the set B, and then finally at the third of these times, which is the time T minus T1 in the set A. And this is exactly, we can just rearrange, if you like, these conditions, which is just the same, obviously, as writing as a T minus T1 being in A, xt minus T2 being in B, and xt minus T3 being in C. So here I have just written the three conditions which define this probability. Just I have written them in a different order, in an order which corresponds actually to the decreasing order of these time points. And this is exactly the claim on the right-hand side, which appeared in the special case when we have 3 time points and 3 events which determine a certain probability in these finite dimensional distributions. So we have seen, in fact, that the process is reversible in the sense of the definition given above, provided the operators P enjoy this symmetry condition with regards to the measure mu. And as a remark, I should probably highlight that the extra condition that mu is in fact PT invariant, this condition is automatically satisfied if the P's are actually conservative. That's an easy consideration, but in general it might be so that the PTs are not conservative. So I promise that we would like to, or that we will restrict the entire discussion to the conservative case, but sometimes I shall nevertheless be slightly more general and allow for the case of explosions. In this case, the reversibility does not necessarily, this property that we have here, the symmetry condition, does not necessarily also imply that the measure mu is in fact invariant. Therefore, if we impose this additional invariance condition, then we can verify the reversibility as we had just shown. So let us fix some notation such that we can use some words in the sequel properly. So let K be a Markov kernel on a general measurable space, and let mu be some measure. Then the kernel K is called mu symmetric if we have precisely this symmetry condition for the induced operator, which is induced from the kernel as an operator on functions, and if this operation is symmetric in this well-weighted L2 inner product, then we call the kernel mu symmetric. That's correct for all bounded measurable functions f and g. And in this case, mu is called a symmetrizing measure for K. And if Pt is a transition function, so a family of kernels, then we call this family of kernels, or the transition function, mu symmetric, if Pt is symmetric with regards to mu for all times t. So in other words, we can say that a Markov process on a general state space is reversible if the initial law is invariant, and if and only if the initial law is invariant, and if the corresponding transition function is reversible, or the correction is symmetric with respect to that transition function. Okay, here we have again this remark that I just mentioned shortly before, that if we have a mu symmetric transition function, and if it is conservative, then mu is automatically an invariant measure. The proof of this is left as a simple exercise. The remainder of this session is devoted to the discussion of a few examples, essentially. First example we want to consider is the case of the Brownian semigroup. And here I claim that the flat Lebesgue measure on d-dimensional Euclidean space is in fact a symmetrizing measure. To check this, I take the inner product of an arbitrary function f in the L2 space with the result that I obtain from applying the Brownian semigroup to an arbitrary function g at time t. Well, this is the inner product in L2 space, and this is the operation of the Brownian semigroup at time t acting on the function g. We know that this is obtained by taking an average perturbation of the initial position by means of a properly scaled normal distribution, or normally distributed random variable. This is what we have here. This is the total expression here is in fact a product integral, so by Fubini theorem I can interchange the order by which I conduct these integrations. This is what I obtain. Inside then the interior integral, which is then just a Euclidean Lebesgue integral. By shift invariance of the Lebesgue integral, I can also move this shift operation towards the argument which is now appearing inside the f function. That's just a translation of the x argument by the square root of t times xi for fixed xi. Now I have almost the same expression as I had before, but now with the roles of f and g interchanged. But however, there's little difference because there's this minus sign here. But I can use the fact that if xi is a standard Gaussian random variable, then minus xi is again a standard Gaussian random variable, so therefore the expectation does not change if I replace the xi by a minus xi because the distributions are the same. And hence I'm ending up here at this expression, which by another interchanging of the Euclidean integration and the expected value yields back exactly the inner product in Lebesgue space, where mu is a Lebesgue measure, of pt acting now on f in the inner product with g. So therefore, in fact, Lebesgue measure is a symmetrizing measure for this semigroup. The next example that I leave also as an exercise is if we have the Ornstein-Uhlenbeck semigroup, which is associated to this stochastic differential equation, then we have already seen that this standard Gaussian measure is an invariant measure. And I claim, moreover, that this is actually a symmetrizing measure. I leave this as an exercise, and as a matter of fact, we will discuss this in a broader context a little down below, but you can also prove and verify this by the explicit representation of the Ornstein-Uhlenbeck semigroup by means of this Miller-type formula. Okay, the next proposition gives a criterion for symmetry of a measure, or whether a measure is a symmetrizing measure or not, in terms of the generator of a semigroup. And here we consider the case of a Feller semigroup acting on a topological space with an associated generator. Then a measure mu in the collection of measures is an invariant measure if and only if it is so that mu integrated against all the functions which are obtained as images of functions in the domain of the generator under the operation A. So with all images, if that's another way to say it, if mu integrates all functions to 0 which are in the range of the generator. So in other words, if the integral of mu against AF gives a 0 for all function f which are in the domain of the generator. That's one way to check. That's a sufficient and necessary condition for invariance, and a sufficient and necessary condition for the fact that the measure mu is symmetrizing is if a similar condition is correct, namely that for all functions f and g in the domain of the generator, the following bracket vanishes, namely if I integrate the g against af, if that is the same as ag is integrated against the f. So in other words, if this operator a, the generator of this function, is a symmetric operator on this L2 space. This is what it says. So we say that we find that the measure mu is symmetrizing for the semigroup if and only if the generator of the semigroup is a symmetric operator in the L2 space, which is associated to that measure mu. I will give only a proof of statement 1, leaving the proof of statement 2 as an exercise. So, statement 1 is a characterization of invariance in terms of the generator of the Feller semigroup. So we start with the direction that invariance implies this vanishing condition on the range of the operator A. So suppose mu is invariant, then we know for all functions f, in fact, that this equality is true. It's just another way of phrasing invariance. And hence, if we take this difference of these two expressions and divide by t, then using dominated convergence and so forth, using the fact that for a function f in the domain of the generator we have actually convergence with respect to the uniform topology, we can pass to the limit of this difference quotient outside of this integration, which then tells us that, of course, this limit or the measure, the integral of this limiting function will be 0. That's easy, and the other way is not much more complicated. If we have a function f which is in the domain of the generator, then we had seen already pretty much at the beginning of our lectures in this semester that we can write down the action of the semigroup on the function f by means of this version of the fundamental theorem of calculus. And since, that's correct if the function f is in the domain of the generator, and in this case we also know that we can interchange the application of A with the application of P. So that's a way to write P, the difference between PT, F and F. That's this time integral. So hence, if we integrate the function pt against the measure mu, which is what we want, we can replace our ptf function by the corresponding expression on the right hand side. So therefore we have this integral of mu against f, and we have, by an interchanging of these two integrations, again by Fubini theorem, we can pull this integration against mu inside the time integral. And if we take a look now at all these expressions which appear inside this time integral, there are these integral brackets, and we know that for a function f in the domain of the operator, the semigroup P maps a function in the domain of the generator back into the domain of the generator. So therefore we can use the condition that A maps all functions in the domain of the generator onto functions which integrate to 0 against mu, and hence we see that the whole integral on the right hand side is in fact an integral over the 0 function. So therefore there is no contribution of that part, and we end up with mu f on the right hand side, which means in fact that mu integrated against ptf is the same as mu integrated against f. That's correct, at least for all functions in the domain of the generator. But since the domain of the generator is closed, the domain of the generator is dense in the set of all continuous functions which vanish at infinity, we find that this equality holds true by approximation for all functions which vanish at infinity and which are continuous, and then by the fact that the functions which are continuous and vanish at infinity generate the full Borel sigma field, we can again by a second approximation conclude that this is correct for all bounded and measurable functions, which is the claim. So therefore we have convinced ourselves that we can characterize invariance of a measure for the action of a semigroup, for a Feller semigroup, say. We can characterize this by saying that the measure integrates all functions in the range of the generator to 0. The second statement, let me say it again, is a characterization of symmetric measures or symmetrizing measures in terms of this generator, which says that the function of correction, a measure, is symmetrizing for the semigroup if and only if the generator is a symmetric operator on the corresponding weighted L2 space. That's a statement which is then also easy to prove, and I leave that as an exercise. We will now use the characterization of invariant or symmetrizing measures in terms of the generator of a fellow semigroup in order to discuss more examples, and these examples will be the most important ones when we discuss models from statistical mechanics or so. Namely, we discuss solutions of stochastic differential equations in d-dimensional Euclidean space, and for simplicity, which is not a very relevant simplification, you can consider the case of two-dimensional Euclidean space if you like, but it can also be D, any D. And so consider the solutions obtained from solving the stochastic differential equation dxt equals v of xt dt plus square root of 2 times dwt, where wt is a d-dimensional Brownian motion and v is an arbitrary sufficiently smooth vector field. And we want to assume that through appropriate restrictions, this stochastic differential equation in fact does induce a proper Markov process. The solutions induce a proper Markov process, and they are give rise to a fellow semigroup. And then my claim is that for this family of solutions to stochastic differential equations, the flat Lebesgue measure is in fact an invariant measure if the divergence of the vector field is 0. But in general, we have no symmetry of this. In general, I claim that this measure L2, or the flat Lebesgue measure, is not a symmetrizing measure for this semigroup. And the second class of examples I want to discuss are these gradient drift diffusion processes, which are the most popular ones in modeling and all other kinds of situations. Well, kind of. There's one big class of stochastic differential equations which are really important, which is what is called the gradient flow dynamics as a deterministic or drift part, perturbed by, again, a Brownian motion in the appropriate dimension. And again, we want to assume that this gives rise to a proper Markov process, a fellow process. And then I claim that the formal Gibbs measure, which is obtained by a weighting of the Euclidean measure, is in fact a symmetrizing measure. So the measure obtained, let me say it again, on d-dimensional space, which is obtained by taking a weighted version of the Euclidean space, of the Euclidean Lebesgue measure, where the weighting factor is the exponential of this h function, then this is a symmetrizing measure. And if you consider the special case of d equals 1, and when h is in fact the square function, or the half of the square function, then you see that this example number 2 entails the case of an Ornstein-Uhlenbeck process as a special case. Okay. In order to prove these statements, these two statements, we shall employ the just established characterization of invariant or symmetrizing measures in terms of the generator. And we basically know what the generator in these two cases is. That is obtained basically by Ito formula. So therefore we have to check for symmetry, and so using the generator, and that will bring up automatically the Gauss theorem in d-dimensional space, which I would like to recall to you. It's the extension of the fundamental theorem of calculus to integrals in higher dimension. And the statement of this Gauss theorem, just to let you know and remind you, is as follows. So suppose you have a smooth, say, bounded domain in Euclidean space, so just some set G, which has a smooth boundary. And suppose you have a vector field, which is defined on this space, as correction on this set, which is a smooth vector field. Then you can compute the divergence of this vector field, and you can integrate that divergence over the set G, so that will be the divergence of a vector field is a scalar function. It's the sum of the respective partial derivatives of the function of the vector field f in the respective dimensions. The sum of all these first order derivatives summed up gives a scalar function. You integrate the scalar function over the set G, and this is just the same as if you integrate the function as a correction of the vector field, the non-differentiated vector field, when taken in the inner product of the normal, the surface normal of the boundary of that domain. So that's the boundary of the domain, and you have, let me write that better. So you have, of course, this is the boundary of the domain, and if the domain is smooth, then at every point you have a notion of a normal. So you take the inner product here. I decided to write the standard Euclidean inner product with a big dot. So you take the inner product of this vector field f in the with the normal vector of that surface, and you integrate that with respect to the surface measure of that boundary. Then these two integrals are the same. So this is this flux picture. So f is something like a flow which transports mass through this domain, and the divergence of this flux measures the total amount of mass being created or destroyed by the flux f. So that's the total mass balance which is induced from this flux, which per second, if you like, and you can equally measure this total mass balance of this flux by just measuring at every portion of the surface how much in that portion of the surface flows in and flows out. That's the net in or out flux which is induced from this flux f. And so by this consideration you find that such a relation must be plausible. Okay, so that's Gauss theorem in d-dimensional Euclidean space. It generalizes, as I just said, the fundamental theorem of calculus. And you typically learn Gauss theorem in your Calculus 2 or Calculus 3 lecture. So therefore we will not discuss it, why it's true, but we have an intuitive understanding why it's correct. So we shall use this Gauss theorem to establish a few integral identities, or actually do what is called integration by parts, which is again a generalization of the classical integration by parts rule that you know from your school, high school times. And we shall, in the sequel, shall again use this bracket notation for just integrals with regards to flat Euclidean measure, and likewise we write just the f in the brackets, which is just the integral of the f function against the Euclidean measure, which is of course also just the inner product of the f function with the constant 1. So here in the integral identities below, we shall essentially work with the bracket exclusively denoting the integration with respect to flat Euclidean measure. And as a consequence of this Gaussian formula, we shall now establish the conventional integration by parts formula. I'll deliver all these intermediate steps to you, which are basically from standard analysis or from PDE lecture. There you do that all the time, but I do not want to assume that you visited any PDE lectures, and that's why I remind you of these facts. So suppose you have now a function f, which is smooth on Euclidean space and which is compactly supported, or let's suppose here this C0 is supposed to indicate that the function f is actually compactly supported, and let f be some smooth vector field. And then I want to integrate the gradient of that function, which is then a vector field. I want to take that at every point take the inner product with that vector field. That gives me a scalar function, and I want to integrate that over the full Euclidean space, where, let me say it again, the function f is compactly supported. So therefore, if the function f is compactly supported, there is a sufficiently large ball that the whole support of the function f is contained in that ball. So therefore this integral is the same as if I do this integration only on this ball, which is a certain compact subset of the Euclidean space. So if I choose the radius sufficiently large, then all the support of the function f will be contained in this ball. And hence this integration and also the support of the gradient of the function f will be contained in the ball, and therefore this integration is just as good if I restrict the integration onto the subset. But now I am in the situation, since I'm doing integration over a compact or a smooth, and in this case even bounded subset of Rd, I can use this Gauss formula, but before I do that, I shall interpret this gradient f times f as a divergence of a properly chosen vector field. I use the formula that the divergence of f, a scalar function, times a vector field, which is a vector field, is, through Leibniz rule, in this case, grad f inner product with f plus f times the divergence of f. That's Leibniz rule for this divergence operator when the vector field of which I want to compute the divergence is actually a product of a smooth function with a vector field. So therefore I see that this part here, this gradient f times f, is a portion, is one component of the divergence of the product. So therefore I can write this integral of grad f times f as the integral of the full divergence of f times f, but what is missing is this extra term, which is needs to be written there. So therefore I subtract this f divergence f to have actually a correct equality. And now here on the left hand side I have exactly an expression to which I can apply my Gauss theorem, which tells me that this full divergence integral of the divergence is just as good as if I do the integration over the surface of the ball, so over the sphere, and I take this vector field f times capital F inner product with the exterior normal of that ball integrated over the surface. But since the ball is chosen large enough, the function f has no more support on that surface, on that sphere, so therefore the function over which I integrate here is the zero function, and what I am left with is just this minus f divergence of f. So as a matter of fact, what I have obtained is I have performed what is called an integration by parts. I was able to map the gradient operator in this integral here, which is a derivative operation, which is a derivative acting on the function f. I have managed to map, or just to put this derivative operation acting on the function f to be, on this little f, to be the derivative operation on the function capital F. That is exactly the same thing that you do, that you learned in your high school years when you want to evaluate an integral f prime g dx. This is modulo boundary terms, which here do not play a role, is the same as minus g prime f dx. That's the one-dimensional formula which you know from your high school times. And this formula that we have here is the corresponding formula in higher dimension, and it is called integration by parts. By the same line of argument, you can also do an integration by parts for higher order derivatives, in particular for the Laplacian operator. And we call that the Laplacian operator, which is always basically showing up, or often showing up, when you consider stochastic differential equations driven by Brownian motion. This is the sum of the Laplacian operator acting on a function f, is the sum of the second order derivatives. And these you can also write as the divergence of the gradient of the function f. So it's just a nested application of appropriate differential operator of order 1. That's what we do here. So I want basically to perform this integration by parts, but not only for first order derivatives, but for second order derivatives. And I can do that as follows, again using Gauss formula, where I suppose that the functions f and g are again compactly supported and sufficiently smooth. So first I write this Laplacian as a divergence of grad of g, and now I'm exactly in a situation. This is, if you like, my vector field capital F, and this is my little f. And by what I've just learned, I can write this also as a minus the gradient of f times the capital F, which happened to be gradient g. So therefore I see that this f integral, f Laplacian g in the integral is the same as minus the integral of the inner products of the two gradients. And of course, I can do that step again, but now with the roles of f and g interchanged, which ultimately consumes again 1 minus, but then maps the second order derivative of the f. So I have managed to map this differential operator of order 2 in the integral to act on the corresponding left-hand side of this product. So therefore, the Laplacian operator is a symmetric operator on L2 space with the flat Euclidean measure, or the Lebesgue measure, as reference measure. And with these two preliminary calculations, I can now finally discuss the two examples which were introduced before. And recall that, okay, so sorry, before I do that, I shall probably, as I see here now, I have a, it's exactly the case that I want to consider. So in our case, if we consider the stochastic differential equation dx equals v of x dt plus square root of 2 dwt, we know that the corresponding generator, by Ito's formula, acting on a function f, if the function f is sufficiently smooth, is v inner product with gradient of f plus Laplacian of f. That's actually the generator. And I want to produce now the formula that measures, or that I need to look at if I consider the symmetry of the operator, of the semigroup. Right, so the question is here in this example 1, the question is whether or not the operator A is a symmetric operator on L2 space when we equip the L2 space or when we discuss the L2 space on d-dimensional functions with the L2 inner product induced from the Lebesgue measure. And so I'll do a first computation first where I check, if you like, for symmetry for this operator. So I'll do exactly and use the formulas that we have established now before to this special case. Writing down the generator acting on the function f when integrated against the function g is just exactly this expression here. So it's grad f times v plus Laplacian of f. So I write this out as two separate points, two separate sums of two different integrals. And I consider these two integrals here on the right hand side separately. First, I want to apply again my Gauss theorem to this guy here when I want to basically get rid of the gradient operator acting on the function f by whatever means. And for that purpose, I want to interpret this, what is written here, as a partial divergence plus or minus correction terms. So therefore, again, by Leibniz rule, I see that this guy, which I have here, is effectively the divergence of the vector field, which is obtained by taking the product of g and f with the vector field v. And what is then missing? By Leibniz rule, there are two terms missing. That's f times grad g v, and there is the product of f g times the divergence of v. That's something that was missing for this divergence part. And the second bracket here, or the second integral, by the integration by parts for the Laplacian operator that I have just seen, is an f times Laplacian of g in the integral. So there's just a straightforward application of what we did before. And now, if the functions f and g, or either of the two, is compactly supported, I can use the Gauss formula to convince myself that this integral here, which is then a boundary integral over a sufficiently large ball, that this has actually no contribution. So therefore, the first integral is actually a 0. And what I'm left with are these terms here. So it's f times Laplacian of g minus f grad gv minus fg times divergence of v. That's what I'm left with. And now, if it is so, which is the assumption in the example number 1, that the divergence of the vector field is 0, I see that also the third part of these integrals does not contribute. And now, if I consider the special case that the function g is exactly the constant 1 function, So my symmetry condition, in a way, collapses to the invariance condition if I replace, or if I choose as the test function here on the right hand side, if I just choose the constant 1 function. So in the special case, this computation, in the case when the g function is the constant 1 function, I see that the gradient of the constant 1 function is 0, and of course the Laplace operator of the constant 1 function is 0. So therefore I see that in fact I obtain a 0 in case when the divergence of the vector field is 0, which is exactly the claim that AF integrated against mu produces a 0 for all functions f which are in the domain of the generator. So therefore, in fact, I have convinced myself that the flat Lebesgue measure is an invariant measure for the solutions to these stochastic differential equations, provided the divergence of the vector field is 0. Now, if I ask for something more, in fact, namely that's also symmetrizing, then what I need to check is the full computation when g is a general function g and not just the constant 1 function. And this discussion was just conducted, and here I have convinced myself that this bracket AF against g integrated against the Lebesgue measure, that by abstract nonsense is of course f integrated against the adjoint operator acting on g, and I have done the computation which told me that the a star of g in this case is a minus gradient of g times v plus Laplacian of g, which is of course different from plus gradient of g v times Laplacian of g. So therefore I have a parity change, but this parity change is of course significant, so therefore a star of g, which I had just computed, does not coincide with a of g. And therefore, the Lebesgue measure here is not symmetric. So it is invariant. That was okay. That was the case when g equals 0. That was something less to ask for. But if we ask for this symmetry condition for general g, we see that this is just not true for general g, and therefore the Lebesgue measure is not a symmetrizing measure. Let's consider now the example number 2 of this gradient drift dynamics. In this case, the generator looks essentially the same as before, but now we are in the special case when the vector field, which we discuss, is a gradient vector field. So the v comes here in the form of a gradient h, of a minus gradient h to be precise. And we want to work with this measure, which is this exponential measure with the h function in the exponent. So therefore we obtain this expression when we want to write it with respect to the flat Lebesgue measure. And now, by the same argument as above, I want to do an integration by parts, and therefore I write this whole thing that I have here as a divergence of g times gradient of f times e to the minus h. So if I do an expansion of this divergence term, what I obtain is a g times Laplacian, which is exactly this part here, and I obtain a gradient g times gradient f. That's the term which I had not seen, so therefore that enters here, which is subtracted for a proper identity. And then ultimately I obtain a g times gradient f times the gradient of e to the minus h, which is exactly this term here. So therefore this identity holds true. And now I can perform an integration by parts in the usual form. Namely, I can map this divergence operation as a gradient operation on this scalar function at the expense of an additional minus. So therefore this term here will be translated into g times gradient f times minus the gradient minus the gradient of minus gradient h, because by chain rule the gradient of e to the minus h is a minus gradient h times e to the minus h. And I see that I get exactly this term here, which cancels with this term. So all that is left after I did this integration by parts is this expression here, which is a minus gradient f gradient g integrated against the measure mu. And I see that this expression here is absolutely symmetric with regards to the roles that are played by the functions f and g. And so I can do the same computation, but now with the roles of f and g interchanged in inverse fashion, which brings f in the inner product with ag integrated against the measure mu. So therefore I see that in fact the generator A is a symmetric generator or symmetric operator when considered in this weighted L2 space with this weighting measure e to the minus h. So I urge you to do this computation again and yourself, because this will be a very important standard case of a gradient drift diffusion dynamics, which we will investigate basically throughout the remainder of this session. All this was preparation effectively to consider this special case, which is basically the most important case of Feller semigroups that we want to consider. Now we want to make a next step away from these Feller semigroups, which is a little bit too restrictive. We want to emphasize the role that is played by this invariant measure, or the role that is played by the symmetrizing measure in either of the two cases. And for that purpose, we pass now to the corresponding L2 or even LP spaces for the further analysis of these semigroups. And in order to set the notation right, we will extend our notion of a contraction semigroup to general semigroups acting on Banach spaces now. And our Banach space that we shall work with below will be the L2 space relative to the corresponding weighting measures, or even LP spaces. For that purpose, we want to use the following general notation. So if we have some Banach space X with a Banach norm on it, and if we have a family of bounded operators on this Banach space, then we call this family of bounded operators a strongly continuous contraction semigroup. If the analog of our Feller semigroup properties hold true, but now in this abstract formulation of operators acting on Banach space, except for a priori the maximum principle, and we want that for each parameter little t, the corresponding operator is a contraction as an operator on this Banach space. And then we want that these operators are strongly continuous, which means that for any x in the Banach space, the operations of tt acting on x converge to x strongly in this Banach norm. That's this strong continuity at t equals 0. And finally, we want that this semigroup property holds true. That's a generalization of our concept of a Feller semigroup to a more general framework. It would just work with Banach spaces. And in Feller semigroup, the Banach space that we work with is the space of continuous functions, which vanish at infinity with the uniform norm, but we might think of other Banach spaces and other contraction semigroups that are there. And in fact, that's what we shall do now. We shall extend our Feller semigroup to L2 semigroups acting on L2 spaces, provided we have an invariant measure. And that's the final concept of today, I guess, namely if we have a topological space and a Feller semigroup on this topological space, and suppose we have some positive measure which is either symmetrizing or invariant, then the claim is that PT, this family of contraction operators, the family of Markov operators, which are associated to this Feller group, induce a unique strongly continuous contraction semigroup on the corresponding L2 spaces by means of extending this operation of Markov kernels now to L2 functions. Namely, we define as usual the TT operation on a function f as the perturbation of the function f by means of this weighting or perturbation of the starting position with regards to these Feller kernels. This operation can be defined for any measurable function t. That gives back a measurable function, and we can also restrict, or we can consider the case when the measurable function is actually L2, say, so square integral with respect to that invariant or symmetrizing measure. And I claim that this operation maps L2 functions into L2 functions, and therefore, and moreover, that this family of operators produce or realize, in fact, such a family of continuous contraction operators on L2 space. And that will be the actual functional space on which we shall basically work for the rest of the lecture. Okay, and the proof of this is basically a consequence of the following contraction property, which then produces all these two other properties by approximation. So what I want to show is that prescription star, that this definition here, that this defines actually really a family of continuous operators which are contractive. So the only thing that's my claim, the only thing that I really need to prove is property 1, and all the remaining properties, namely properties 2 and 3, will basically be a consequence of the corresponding property for the Feller case, using approximation of an arbitrary L2 function by continuous functions which are vanishing at infinity. So therefore I emphasize, or I restrict the discussion here to the proof that these operators are a contraction. Okay, so the important tool that we shall use is the Jensen's inequality. Namely, if we have this operator Tt acting on F, evaluating at position x, and here in a way I shall assume that the kernel is Markovian or is really conservative. The argument for sub-Markovian kernel is the same, essentially. So this is again writing out the operation of the operator T acting on the function f. And this is an averaging procedure. So for fixed x, this is taking the expectation of the function f with regards to the probability measure induced on E through this kernel. And for probability measures, I have a Jensen's inequality or Hilde inequality, which tells me that this integral is less or equal to integrating the square of the function f and taking the square root of that integral. This is Jensen's or Cauchy-Schwarz or Hilde inequality. And this is the important step. So hence, if I now want to compute the L2 norm in this weighted L2 space of the function which I obtain after I apply the T operator, then okay, right, I read first what that actually means. This is the TT operator acting on the function f, taking the square of this and integrating against the measure mu. Now that's a non-negative function, and by Jensen's inequality I have a pointwise upper bound for this. Jensen's inequality tells me that for each position x, this number here, which is integrated, is bounded from above by the function which is obtained by applying to the square of the function f, the TT operator. And now I have got rid of, if you like, of one of the two instances of the t, and I can absorb this t. This appears only twice, if you like. Here we have an inner product of t acting on f with t acting on f, which basically means that the t operator appears twice. But here I have managed to give an upper bound in terms of of something which involves only a one-time application of the t. And now if the mu is invariant, then of course I can map the tt onto the mu or basically forget about it because it does not have any effect. So therefore this guy here is exactly just the L2 norm of f in this weighted L2 space. Or if mu is symmetric, then I can write this TTF squared, so TTF squared integrated against the mu. Of course, I can write this as a TTF squared with the inner product, with the constant 1 function integrated in the L2 inner product. And then I can use the symmetry of T to write this as an F squared TT1 mu, but TT1 by sub-Markovian property is no bigger than 1, so therefore I get an upper bound also in this case by replacing the function TT1 by the 1 function, such that in both cases I get an upper bound of the integral of the square function of f with regards to against the measure mu, which is of course the L2 norm of f squared. So hence I see that this operator TT is in fact a contraction in this L2 space, and property 1 is established. So I do have in fact a contraction semigroup in case when the measure mu is a symmetrizing or an invariant measure. And the remaining properties 2 and 3 basically follow from the corresponding properties of the Feller semigroup by extension to the L2 case. That's the extension of this TT guy, this new semigroup, which is now a semigroup acting on a bigger space, essentially, is called the L2 mu realization of the Feller semigroup. So I have managed to get a bigger picture of my semigroup. I have managed to basically extend this Feller business to now a function space in an LP function space. And similarly as in the Hiller-Yoshida theory for Feller semigroups, I can invoke a Hiller-Yoshida theory for abstract contraction semigroups. So therefore I can talk about the corresponding generator, which is the generator for the corresponding L2 realization of this semigroup. And this is the L2 mu, the so-called L2 mu generator of this semigroup. So it's an extension. So in pictures you might consider the following, that we have a certain topological space E, and for this topological space we can consider all possible measurable functions. So if you like, this would be the full space here would be all possible measurable functions. So that's that's the symbol for all measurable functions is sometimes L naught of the topological space E. So that's a huge space of all possible functions, and in this collection of all possible measurable functions on E, we have a certain subset, which is this collection of all continuous functions which are vanishing at infinity. And in this subset, we have a further subset, which is the domain of our Feller generator. And here we can do Feller semigroup theory. But all these sets sit inside a larger space, which is, if we have found an invariant measure, for instance, then we can consider the corresponding L2 space of functions which are square integral with respect to that invariant measure. That's in larger space in general than the functions which are continuous in vanishing infinity, of course, if the measure mu is finite, for instance. And we can, by approximation, extend our semigroup. We can extend also the generator, and the generator of this extension has a domain which is larger than the initial domain of the initial operator. And in the sequel we shall mostly work, when we want to study analytic properties or statistical properties of this Markov process, we shall for the most of the time work with this extended semigroup, because it produces a little more flexibility regarding measurability and continuity properties. And we shall also work with norms, LP norms and so forth, which are more natural to consider on these extended spaces. So therefore it turns out to be convenient to work in this extended space when we want to do analysis of these operators. In a way, for the construction of the process, that's how you should look at it, for the construction of the process, you typically use the Feller picture, which is this restricted functional analytic framework, because there you can use this duality between measures and functions, which allows you to get the transition function. That's an important piece. So if you want to construct a process, you need the transition function, and that can be obtained in the easiest fashion when working in the Feller theory, in the actual Feller theory on continuous functions. But after you have constructed the process, when you want to investigate further properties, then you typically pass to this extension of this Feller theory to this functional-analytic LP spaces, because there it's easier to work with and it's not so rigorous in a way. It's not so delicate. Okay, that was an important conceptual step, and from now on we will mostly work in this function space world with LP functions.